Alrighty guys, welcome to Circular Motion. Today we're going to be talking about the relationship between the change of velocity over time and acceleration, how to derive tan theta equals v squared on rg for a bank road, and some different types of centripetal forces. So you'll see in front of you here we have a circular path, and what we're going to assume is that this thing's moving that way. So from my side it's moving clockwise. So we're going to consider 2 points on this circle. We're going to have a point just here, and we're going to have a point just here. Hopefully you guys can see those reasonably well. I'm going to draw some vectors on there in a sec anyway. I'll steer right. So for the first point, so this point here, it's got a velocity vector heading in about that direction. The second point has a velocity vector in somewhere around about that direction. Now, it's important to note that speed is constant. Notice I haven't put a vector line above that because it's not a vector, it is a scalar, so it's constantly changing direction. Speed is constant, velocity is definitely not, and it's tangential, so I'll go, it's right angle to the circle itself, so it's always at right angles to the circle. Now, if we want to make something move, make something change direction, not speed up, not slow down, we have to apply some sort of acceleration. We're always going to be applying some sort of force to some sort of mass to affect that change. Now, if we want something to not speed up, not slow down, but always change direction, this acceleration, therefore this force, has to be in a very specific direction. And to work out which direction that is, we can use some vectors on here. So I'm going to go to orange now. So we're going to look at we've got I, and we're going to look at F. So VI, VF. So if we want to find out the acceleration that anything experiences, what we're looking for is its change in velocity with respect to time. So hopefully you can remember that's V final, take V initial. So its final velocity, take its initial velocity. Now, direction is obviously very important here. So if these two things were the same size, we still have some sort of, might not speed it up or slow it down, but they're vectors. We do have a vectorial nature here, so we can look at the vector addition. Now, if we're looking at VF, VI, how on earth am I going to get VF take VI? Well, we can sort of play around with a little bit of maths, and we're going to do VF plus the negative of VI. So now what we've got is we're adding together, so vector addition, the negative of VI to VF. And what that's going to look like is, so here's our initial, so that's VI. Our negative VI is the exact same length, parallel, but in the opposite direction. So that's the opposite direction. So here's VI is minus VI. So what we need to do is get this one, add the opposite one of that to it. So I'm going to pick up this one here, this vector, and I'm going to dump it here, but I'm going to put the arrow on the other end. So here we go, here's my best impression of that. It's actually not too bad. So the change in velocity is the leftover bit. So the change in velocity is that guy there. That's the direction of the change in velocity. Now if I was to scale this up and draw a dotted line like this and make that reasonably straight, you would probably see that that goes through the center of the circle. So the direction of the change in velocity is towards the center, which means that the acceleration is obviously towards the center, so there must be some sort of force towards the center, because it's not going to accelerate where there's in a different direction to where the force is applied. So I'm going to change the velocity in a different direction to that which it's accelerating in. What this means is that we can have a centripetal force. So the centripetal force is keeping the speed constant, and it's perpendicular to the motion of the particle, the object, whatever it is that it's moving around. So what it does is provides a centripetal force, provides a centripetal acceleration. So in this case here, the centripetal force provides a centripetal acceleration, and you'll generally see it written with a little subscript c, so then that's a special case of forces In this case here, what that means is that it's not going to speed it up, not going to slow it down, it's constantly going to change direction, and it's always changing its direction towards the centre of the circle. Unfortunately, it never gets there because it's always sort of moving past as it's changing direction. Alright, on the equation sheet you'll probably see something like this. So the size of the centrifugal acceleration is equal to v squared on r. This v here is the scalar one, it's the speed. So if we were to have a large acceleration, we've either got to have small radius, so turning a tighter circle, that makes sense, or we've got to have a smaller radius, smaller corner, going the same speed around a small corner in a car as opposed to a big sweeping bend in a car. The smaller corner requires more force, more friction, or we're going faster around that same corner. So a larger speed means a larger centrifugal acceleration. Now, on the topic of cars driving around cars, this is why road authorities, transport authorities all around Australia bank some corners. So you'll notice on especially country roads with 80 km/h speed limits on some of the corners that the 80k suggested speeds around some corners, the road won't be flat and level. The road will be slightly cambered or slightly banked, like the banked track of a velodrome, for instance, or a NASCAR track, or a BMX track, or something like that. So instead of you having your car front on like this on a dead flat road, we have two forces acting here. We have a gravitational force, mg, and we have what's known as the normal force. Now the road can't push sideways on the car, it can only react to sideways forces, or it can only react to forces. At the moment it's going to react to this gravitational force, which is straight down, by supplying a normal force in direct opposition to that, so that the car's on a nice flat bit of road, it's not sinking into the centre of the earth. Now when we have a banked road, don't need an arrow on that, don't need smudges either. When we have a banked road, what we have is some angle theta. So now our car is, so this is a car front on, it's not a car driving up the hill below. We still have that same, supposed to be the same car, we still have that same gravitational force downwards, and we still have a normal force. Now remember, the normal force is perpendicular, so normal force is perpendicular to the surface, or to the road in this case. So it can't push straight up, it can only push perpendicular. Alright, that normal force has to still cancel out gravity, otherwise we're going to be sinking into the road. So the vertical component of the normal force is equal and opposite to the gravitational force. Now what that means is that we've got this tiny little bit of leftover, and this tiny little bit of leftover is directed, as you can see, hopefully towards the centre of the circle here. So as this car's driving around this banked track, there's going to be a force that's helping it steer to that way. I want to say left or right because that's my right hand, not my left hand. So what it's going to be doing is like banking, which is helping it turn the corner. Sorry, trying to get ahead of myself here. It's going to help it turn the corner without relying on friction, or you can still rely on friction, but you can therefore go a little bit faster. So the 80k/h suggested speed limit analogy comes back because we have this. It's a little bit safer to go a little bit faster around some of these corners. Now what we need to do is work out where theta exists, and we can do some geometry type stuff, but that's what Year 7s do, so we know how to do it. There's theta, so alternate angles, corresponding angles, whatever you want to do. Here's theta, here's theta. We've got to work out what on earth tan theta is. So tan theta is opposite over adjacent, and in this case our opposite is the centrifugal force, and the adjacent is mg. Direction, we're not worrying about the negative mg, whatever just yet. Now, back to the centrifugal force. You notice if you rewind 5 minutes, you would have seen centrifugal force causes some sort of acceleration. But we also know that F equals ma. On your equation sheet, you'll see A centrifugal acceleration is v squared on r. So now what we've got is, so Newton's second law and the centrifugal acceleration, mv squared on r. So this here, Fc on this top line, becomes mv squared on r. Is mv squared on r over mg. Alright, so there's two ways you can simplify this. We can cancel some m's and smush the r and the g together, or we can look at it in a slightly different way. And it's probably easier to look at it in a slightly different way. So this case is mv squared on r times by 1 over mg. Because if we divide by anything, we're really multiplying by its reciprocal. Now it's a little bit easier to see. Those two go away, the 1 disappears, the g and the r go together, so now we're left with v squared on rg, just like we're hoping to find. Now you'll notice one of the things cancelled out, mass. So in this case here, it doesn't matter if this is a truck, bus, car, bike, train, doesn't matter what it is, aeroplane, except bank road, the bank the wings, and it doesn't matter what it is, that mass cancelled out. So over here, the mass cancelled out on the top and the bottom line. So the mass of the vehicle is irrelevant. There is a set speed for any banking angle, there is a set speed for a radius, that's g is gravity. So for any radius of curvature and any banked angle, there is a speed at which you can drive around that, take your hands off the steering wheel, take your hands off the handlebars, whatever it is, and you'll steer around that corner just relying on the on the centrifugal force rather than any friction. I do not advise you doing this, okay? However, physics says it works, so it must do. Other things that may cause the centrifugal force, so we've got friction, we've got gravity, so when we're keeping satellites and stuff in orbit, we've got the banked roads. A little bit later on in the course we'll talk about magnetic fields, and they also cause charged particles to go in circular motion because they're forces acting right angles to the motion. So, quick recap. The direction of the change in velocity here, which is the direction of the acceleration, which is the direction of the force. I just spotted these. There we go. The direction of all of those things is towards the centre of the circle. We can have anything like friction or gravity or bank roads or magnetic fields that could cause that centrifugal force. The centrifugal force has to be constant in size and it has to be perpendicular to motion. Alright, if it's not those two things, it just won't work. It won't be, it might go around a corner, but it's not going to be constant, uniform circular motion. Alright, so in order to be uniform circular motion, uniform means the same, circular means circle, motion means moving. And for those things to be ticked off, it needs to be this, and it needs to be this, and it can be caused by any of these things over here. Alright?